x86 and ARM, two processor architectures that power everything from high-end gaming PCs to smartphones. But how do they really compare? Why does x86 dominate desktops while ARM is taking over mobile and even some laptops? And what do their assembly languages look like? In this video, we'll break down the key differences, compare their assembly code, and explore what the future holds for both. Let's get started. x86 assembly refers to the low-level programming language used for processors based on the x86 architecture, originally developed by Intel in 1978 with the 8086 processor. It follows the CISC or complex instruction set computing design, meaning it has a large and feature-rich set of instructions. x86 has been the dominant architecture for PCs, laptops, and servers, with companies like Intel and AMD continuously improving its performance. x86 assembly code interacts directly with the CPU's registers and memory, making it useful for high-performance computing, operating systems, and low-level programming tasks. If you're unfamiliar with assembly concepts like instructions, CPU registers, and memory operations, check out our separate video on assembly basics. Now let's take a look at ARM assembly. ARM assembly is the low-level programming language for processors based on the ARM or Advanced RISC machine architecture. Unlike x86, ARM follows the RISC or Reduced Instruction Set computing design, meaning it uses a simpler, more efficient set of instructions that require fewer cycles per operation. This makes ARM processors highly power efficient, which is why they dominate smartphones, tablets, embedded systems, and even some modern laptops, like Apple's M-series chips. ARM assembly has a consistent instruction format and a larger set of general-purpose registers, making it different from x86. Now let's take a look at their instruction sets. One of the biggest differences between x86 and ARM is their instruction set architecture, or ISA. As mentioned, x86 follows the CISC model, which includes many specialized instructions that can perform multiple operations in a single command. For example, in x86, this line multiplies two registers in a single instruction, whereas ARM's RISC model requires simpler instructions, such as the following, which performs the same operation but follows a more uniform structure. Another key difference is memory access. x86 can manipulate memory directly, while ARM requires separate load and store instructions. The difference in instruction sets affects everything, from performance to power consumption, and even how developers write assembly code. Next, let's see how they stack up in performance and energy efficiency. When comparing x86 and ARM, performance and power efficiency are two of the most notable differences. x86 processors are designed for high performance, often found in desktops, laptops, and servers, where power consumption isn't always a top priority. These processors typically feature higher clock speeds and more complex instructions, allowing them to handle demanding tasks quickly, such as running resource-heavy applications and games. On the other hand, ARM processors are built for power efficiency, making them ideal for mobile devices and embedded systems, where battery life is crucial. ARM's simpler instruction set and low power consumption allow it to deliver decent performance while using less energy, making it the go-to choice for smartphones, tablets, and other portable devices. So, while x86 excels in raw performance, ARM shines when it comes to balancing performance with energy efficiency. Now, let's talk about compatibility. Compatibility is a crucial factor when choosing between x86 and ARM. x86 has long been the standard for general-purpose computing, meaning most operating systems, applications, and drivers are designed to work seamlessly with it. This makes running legacy software and a wide range of modern programs effortless. ARM, however, follows a different instruction set, so software built for x86 doesn't run natively on ARM without modifications, recompilation, or emulation. While some operating systems, like Windows and Linux, offer ARM-compatible versions, many applications still require adaptation. This difference in compatibility also extends to peripherals and drivers, as x86-based systems often have broader support for external hardware, whereas ARM devices may require specialized drivers. While ARM's ecosystem is expanding, x86 remains the more universally compatible architecture, especially for users relying on a diverse range of software and hardware. Now, Let's compare x86 and ARM with a simple example. Here is a short snippet that adds numbers from 1 to 5 and stores the result in a register. While both snippets achieve the same goal, there are key differences in how each architecture structures the instructions. x86 has a dedicated inc instruction for increment, whereas ARM does not, requiring an add operation instead. Similarly, x86 uses JL or jump if less for conditional branching, while ARM uses BLT or branch if less than, which relies on status flags set by CMP. These differences illustrate how x86 often provides specialized instructions for common tasks, while ARM relies on simpler, more general-purpose operations. Despite these variations, both architectures follow the same logical flow to complete the task. It should be noted that both x86 and ARM architectures power a wide range of real-world applications, each excelling in different areas. x86 processors are commonly used in performance-intensive applications such as high-end gaming, video editing, and large-scale data processing. For example, game engines and 3D rendering software are often optimized for x86 due to its ability to handle complex calculations efficiently. On the other hand, ARM is widely favored for low-power, always-on applications, making it the backbone of embedded systems, IoT devices, and even some cloud computing solutions. For instance, smart home automation systems, wearable health monitors, and battery-powered security cameras frequently rely on ARM processors for their energy efficiency. Additionally, ARM's increasing adoption in server environments and even personal computing shows how its capabilities are expanding beyond traditional mobile and embedded uses. In conclusion, x86 and ARM assembly each have their own strengths, shaped by their design philosophies and intended use cases. x86 excels in high-performance computing, offering a rich instruction set and broad compatibility, while ARM prioritizes power efficiency and scalability, making it ideal for mobile and embedded systems. Understanding these differences is crucial for developers working with low-level programming, performance optimization, or system architecture. As ARM continues to expand into areas traditionally dominated by x86, and x86 adapts to power efficiency demands, the line between them is becoming less rigid. Whether you're developing software, optimizing code, or simply curious about processor architectures, knowing these distinctions helps in making informed choices in an evolving tech landscape. That wraps up our comparison of x86 and ARM assembly. If you found this video helpful, consider subscribing and giving it a like. Check out our other videos on programming, computer architecture, and tech concepts. Follow us on Facebook and Instagram for more updates. Thanks for watching.